Okay,
There you
well,
are.
welcome to the Air Sea Fluxes from Space webinar series. Today, we're going to hear about the Planetary Boundary Layer Initiative. Um, and how do you say your name? I'll let you introduce yourself.
Oh, my first name is Joao. Last name is Teixeira.
If you want to share.
Yeah, don't
So,
worry about it.
well,
It's.
welcome
Don't worry about it.
and take it away.
Thank you so much. Thank you so much for the invitation. So what I have here today is a presentation about this global PBL observatory. That's how we sort of calling it for the moment. Um, and I'm going to focus on the boundary layer over the ocean. This is not going to be an explicitly sort of air-sea interaction presentation, but there are a lot of connections to air-sea interaction directly and explicitly, and a little bit less so sometimes. Um, so it's mostly about the boundary layer. I'll introduce some science aspects of it, and I'll talk about what we're thinking in terms of a potential observatory, potential mission. So now we all know, I mean, I'm not, some of the slides I'll go quickly. You, of course, all know the critical role that the atmospheric PBL plays in sort of the mediator between the air-sea interface and the full atmosphere. And I'll go to the next slide with my mouse. So it's this most turbulent layer adjacent to the Earth's surface. It connects not only the ocean to the atmosphere, it helps connect, of course, the land surface and the ice surface. And in that sense, plays a big role in modulating the interaction between these different Earth system components. It also plays a critical role in a bunch of very important applications that you all are well aware, from weather prediction, where air quality and dispersion of pollutants, climate, famously things like cloud climate feedback the PBL plays a fundamental role in that. And in recognizing that about 10 years ago, 8 years ago, when it came out in January of 2018, the 2017 National Academy's Decadal Survey for Earth Science and Applications recommended the PBL for a potential mission. So recommended it in like a third level category for incubation, and I'll show that. But it was on this table that said, okay, these are the things we need to observe from space in the next, in our case, not the next 10 years, but kind of in the next 20, 8 years ago. Now, it didn't start with the Decadal Survey. A lot of this started with a bunch of us organizing meetings and workshops a long time ago, started a long time ago. This is a photo of a workshop that I organized together with Yak Young and Rob Wood at Caltech as part of the Keck Institute for Space Studies, one of the first workshops of the Keck Institute. And this one was about innovative satellite observations to characterize the cloudy boundary layer. And we started building a community that didn't really completely exist. I mean, of course, the boundary layer is an enormous community that's thousands of scientists across the world studying the boundary layer. But the idea of having a sort of a NASA community, or at least a community focused on PBL from space, was relatively new. I mean, there were, of course, many people, including myself and others, doing bits and pieces here and there, but wasn't really a community per se. So we started this process about 16 years ago. And the Decadal Survey happened. Many things happened, of course, between this workshop and the Decadal Survey. But going back to the Decadal Survey, and many of the people you can see in this picture are still involved very much in the boundary layer science, and many of them in what we're putting together right now. So in the Decadal Survey, what we had was a big 700-page document, but one of the things that it does is that it provides a table that kind of summarizes where the national academies and the committee feel that we need to move forward towards to. And in that table, there's basically 3 levels of categories. Top level world missions that we really need to fly in the next 10 years. Then there were a series of suggestions for what they call explorer missions. So these were topics or measurements and topics that could be competed. And then there was a bottom line of 2 or 3 missions, including the PBL, what they call it targeted observables, not missions, including the PBL for incubation, which means, we don't know what the right technology is. So we need to spend some time and money thinking about how we're going to go about doing this. And the PBL was put in that category. And in particular, better profiles, so more accurate and more and finer resolution profiles of temperature and water vapor and the PBL height were sort of the main targeted observable, the PBL, but essentially the thermodynamics of the PBL. And so at the time, the main question, of course, was, and that's what we spent quite some time thinking about, which measurement approaches and architectures of combining different ones. And I mentioned that coupled with sort of modeling and data simulation and other data science aspects would optimally address the PBL science requirements. And after the Decadal survey, NASA competed. There was a call for people to volunteer to propose to be members of a science team. And the science team was in charge of putting together a PBL report, incubation report. The report actually it came out in 2021. You can see at the bottom there's a PDF that takes your PDF link or a link to a PDF directly to the report, or you can just Google NASA PBL report and you'll find it as well. There's a summary of that report that came out just 6 months ago in BAMS that sort of kind of summarizes the highlights of the report. Now, one thing that NASA likes to do is this idea of traceability matrix, right? And the idea is that you start with sort of a vision and science goals, science topics, you go from left to right, and at the end you get the measurements that you need to make. And we, it's not always easy to do, and it's not always obvious that you start from the left and go to the right. There's a lot of iteration between left and right. But in the report, we have an attempt to create this science traceability matrix. The only one I'm going to show here is this one, which sort of gives you a very brief overview from a sort of high level of what the vision is and what the science goals, and then what some of the science topics were. And the vision is, following the Decadal survey, really trying to characterize the thermodynamic structure of the PBL better. We divided this in 4 science goals. 3 of them very topical, and one of them is more of an applied one connected to modeling and mixing and air quality. But the first 3 are essentially about the interface between the boundary layer and other very important entities of the climate system, in a way, or interface between temperature and water vapor in the boundary layer and other entities. One is about sort of the interaction between the PBL and deep convection. The second one is clouds and the PBL. And the third one is the interaction between the PBL and the surface, land, ice, or ocean. And you can see that in the science topics. I'm not going to go into the details and lists and anything like that, but in the science topics, you can see that one of the aspects that is highlighted as a topic is water vapor near the surface. And we will touch on that, and I will have at least a few slides sort of highlighting the fact that some of these measurements that we propose, or that kind of already exist somehow, and some new ones will provide measurements of the water vapor much closer to the surface than we are able to do today with sort of infrared or microwave observations from space. Now, what I'm going to do with the science is I'm not going to give you a list, and I'm not going to try to prioritize in sort of a more formal sense like we did in the PBL report. And there's science chapters like 30 pages and a lot of information there. But I'm going to talk to you about 3 kind of stories, short stories that highlights, that tries to focus our attention to what kind of vertical resolution do we need, what kind of horizontal resolution do we need, and what kind of combination between the 2 do we need, by looking at science questions that are quite sort of pertinent for weather and climate science. And the first one is about PBL clouds. And so most of you probably, if not all, of course, know very well that one of the great uncertainties in climate prediction or projections today is the role of clouds. So we don't really know how clouds are going to respond to climate change, and we don't know how much clouds are going to modulate climate change, right? But we do know that a very small change of a percentage of a cloud in globally can affect the top of the atmosphere, shortwave radiation, the reflective one, and in that sense affect the balance of energy coming in and leaving the planet. So the clouds can be quite critical for the climate system. We don't understand exactly what the role that clouds will have as climate changes. And that, of course, hundreds of studies and a lot of attempts and using a variety of different tools, from observations to models to theory, But one thing that people have been looking at is the idea of how what is the essential aspect that controls clouds in the PBL, at least in the tropical and subtropical oceans. And in that context, if we understand that connection, if we understand what is the essence of what controls clouds, then we may be able to understand better what happens to clouds and how clouds will modulate climate change. And one line of thought has been this connection between the amount of clouds with sort of the stability of the atmosphere. So in that case, we define stability or low tropospheric stability as the difference between potential temperature in the atmosphere at about 3 kilometers above the surface and the sea surface temperature. And since at least Neighborger, who was a faculty at UCLA, and I think so, at least since the 60s with Neighborger, but I presume even before that, I think there were some German studies in the 20s and the 30s. People have observed that there is, at least from a climatological perspective, a relationship between the cloud amount and the stability. So the more stable the boundary layer, the more cloud cover it contains. Now, one question that many of us have asked over the years is, we have all this empirical evidence, but can you actually derive this theoretically from first principles? Can you go back to the first law of thermodynamics or something similar to that and come up with an answer to this question about the theoretical derivation? If that's the case, then where can that take us, right? And one of the tools that we use in PBL science a lot, and many of you do as well, I'm sure, and it's been used in the ocean as well, is large eddy simulation models. So I'm not going to, I'm pretty sure you all know about large eddy simulation models. I'm not going to spend too much time on that, but the critical thing, of course, to highlight is that these are, filtered versions of Navier-Stokes equations. Because we zoom in on smaller domains, like in this case, 20 by 20 kilometers, we can have very high resolutions of the order of 10 by 10 by 10 meters in this case. And because of that, we can resolve, depending, of course, on the type of boundary layer, things are different if the boundary layer is more stable or more convective. But in general, the idea is that LES models are able to resolve, let's say, 90% of the essential terms and convection. And of course, you still need closures for representing the subgrid scale flow within the grid box, but those tend to be simpler than what you need to do for an ocean model or an atmospheric model. And the figure here is just to highlight the fact that LES models today are very powerful and very realistic. This is a depiction of clouds from an LES model, and the clouds look extremely realistic, and the brain doesn't fool us there, because it in that sense you can understand the complexity that these models are able to represent. So what we did in this case, so Daniel Chung and a bunch of other people, what was done here was to use an LES model, and this was the study to try to understand where does this low tropospheric stability relationship with cloud amount could come from. And in this case, we used 10 LES studies of 10 different types of boundary layers. You can see at the top, each column is one type of boundary layer. We can start from the left with colder SSTs. You have this sort of stratocumulus boundary layer. So this is a view from the top, and that over here in the bottom row is a view from the side. So you go from stratocumulus boundary layers to cumulus boundary layers to the right when the SST is about 300K. And by studying, looking at the data, the steady state simulation, the steady state results of these simulations, we can actually try to understand what terms in the first law of thermodynamics are important and which ones control the transition from, let's say, stratocumulus to cumulus clouds. And I'm not going to dwell on the equation very much, but you can see that what you have here is an Eulerian tendency of a temperature variable. In this case, is the liquid water potential temperature. One of the sort of confusing aspects of for people when we often give talks about the atmospheric boundary layer, particularly when it involves clouds, is the fact that there's all sorts of different thermodynamic variables that are not always easy to explain in 30 seconds. But think of this as a potential temperature variable. Don't worry too much about the detail. I'm happy to clarify things if you want at the end or by email. But and to the right, you have the different terms that are important for the balance of this liquid water potential temperature. And essentially, there's two terms that basically change as you move from stratocumulus to cumulus. One is this subsidence term, this sort of vertical advection of the mean values of liquid water potential temperature, and the other one is the vertical divergence of the radiative flux. And in reality, what happens is that as the clouds change, the vertical structure changes. Now, there is no cause and effect here. We're looking at steady state simulations and different sort of regimes, but by looking at the balance of energy, we did notice that there is this balance between the vertical structure of temperature and the cloud. And cloud is involved in this equation over here because it controls the radiative fluxes at the top of the boundary layer, and the vertical structure of temperature is over here. So in the end, if you actually integrate from the vertical up to, in vertical up from the surface up to 3 kilometers, you can come up with numbers. I'm not going to show the numbers, but show you very simple synthesized version of the equation, which is that changes in the cloud top radiative cooling balance or are balanced by changes in the subsidence warming. So if you actually, because this is an integral over here, sorry, because what we looked at, it's at the vertical integrals. If you calculate the first order integral of this component over here, the subsidence, you end up deriving exactly this sort of low tropospheric stability equation in which the cloud cover or cloud fraction is a function of the difference between potential temperature at 700 hectopascal, 3 kilometers in the sea surface temperature. And you can see this is the same. This figure is very similar to the figure over here. This is a figure obtained from climatological observations. And you can see the cloud amount versus this stability, this boundary layer stability term. And over here, you can see the same thing coming out from the large area simulation experiments. And so this, what comes out is that this LTS relation is just the first order approximation of this much more complex relation. And that the first order integral leads to this linear relation between cloud cover and boundary layer stability. And if we want to explore higher order theoretical versions, so if we want to go beyond the sort of the trapezoidal approximation for the integral, and you want to go to higher order, second, third, fourth order, and try to explore the implications of something like this, and try to explore the implications of this very basic theoretical derivation, then we would need global observations of much higher vertical resolution PBL temperature profiles, right? Because while this LTS relation assumes that you only need two pieces of information, if you want to go to higher order versions of this equation, you would need more than that. Now, this is one justification, of course, for higher vertical resolution associated with science questions, associated with climate change, associated with the role of PBL. From practical purposes, and we'll debate that, and I'll show you a couple of figures. The idea that we need higher vertical resolution is, of course, very well accepted in the sense that, yes, we need higher vertical resolution to depict structures that we can't do otherwise for a variety of applications. This is not the only one. Another story I would like to briefly talk about is this idea that in atmospheric models, both used for weather or seasonal prediction or climate prediction, a lot of different physical processes are represented by different algorithms, by even different routines. And over the last 15 years, there's been sort of a critical shift that is taking place, that there's more and more groups trying to sort of unify or integrate turbulence and convection parameterizations and try to come up with models or parameterizations that basically represent each one of these different mixing processes in the atmosphere in a sort of unified way, in an integrated way, by using the same set of equations. Essentially, stratocumulus or dry boundary layers or deep convection are just different sort of manifestations or realizations of a highly turbulent flow that interacts with phase transitions and with radiation in a very important manner. And so in that sense, it's only natural to come up with these sort of unified approaches to represent convection in the boundary layer. And at the heart of each one of these ideas is an idea about how the properties are distributed in space. So you can imagine that inside the grid box, you're trying to, an horizontal grid box, lat, long, or X, Y, you're trying to come up with equations that depict how the smaller scales that are not resolved by the model behave and how they interact with the resolved scales. And different parameterizations or different approaches assume different types of distributions. For example, higher order methods like CLUB assume that the PBL mixing is basically, PBL thermodynamic properties are basically represented by joint double Gaussian PDFs of temperature and humidity, while EDMF, which is another common parameterization that tries to sort of unify different regimes, assumes that you can represent nature by a sort of a joint Gaussian PDF plus a variety of discrete convective elements that populate different parts of sort of the phase space. So we would need new but high horizontal resolution global PBL observations of thermodynamics from space to actually clarify which approaches are closer to reality, any of these is, or new ones are necessary. And so trying to represent sort of the subgrid scale processes better in atmospheric models, for the PBL at least, deeply depend on our ability to provide new global high horizontal resolution observations. Now, another story, the last story here is about, the first one was about vertical resolution. The second one is about horizontal resolution. This one is about combining the two and how, what is the role of the vertical structure versus the horizontal structure. So if you think about a grid box and you assume that you can do, the bar over here are averages, these are the primes are perturbations. So if inside a grid box you want to write a generic equation with no horizontal advection or vertical advection, just the Eulerian part for conserved scalar spatial variance, you end up with something like this, right? So the Eulerian tendency of the variance or covariance is a function of the divergence of a third moment plus this production or consumption term minus this sort of dissipation term. And if you assume steady state and you neglect the third order term and use that diffusivity for fluxes for simplicity in a way, you end up with something very simple that basically would relate for the potential temperature and the water vapor or the total water. So it would relate the variance, the horizontal variance within the grid box with the vertical structure, so with the vertical gradient of the mean. And so one question that you can pose is how realistic are these approximations and how do you actually validate this type of approximations? How often does this happen in nature? And one argument is that, well, we could try to use LES synthetic data to validate these approximations at smaller scales, and I'll show you a slide on that. But for the global perspective, we would need satellite observation. So LES are extremely powerful tools, but because we need to use them in very small domains, otherwise we lose the ability to depict things with very high resolution. We can't expand them to the whole globe, and it's very difficult to expand them to very large regions as well. So we would need to rely, even if we trusted LES very much, we still would need to rely, of course, on observations for larger scales. There are other issues with LES that we don't necessarily would trust them at the medium scale, but that's a different part of the story. So, one approach that you could think moving forward would be to then use satellite observations to investigate these sort of approximations at scales bigger than 1 kilometer. So here we come with, here's a number that kind of defines in a way what sort of scales we would need to be able to resolve to look at these connections between horizontal variability and vertical variability. Now, continue along this line just for another second. One thing that I just mentioned that we did was to try to look at this relation, this steady state relation between the spatial variance in the horizontal and the vertical gradients from an LES perspective, right? So what we're trying to do here is to look at this two relationships over here and see how valid they are. And one way to do that is to calculate what the variances are in two different ways. One, we calculate the variances basically using all of the data that we have from the LES and basically just, some statistical exercise. And you can see that over here on the right as the full line for both temperature, potential temperature and water, total water in blue. These are two regimes that we're simulating. So the top one is shallow convection. So we go back to this figure over here. This is a stratocumulus regime, fully covered by clouds. This is sort of the popcorn shallow convection regime. And if we go back to our figure here, this is sort of the shallow convection. So this is the right-hand side of, it's not the same LES simulation, it's a different one, but doesn't matter. It's the same case, kind of. This is for shallow convection. This is for stratocumulus. These are the liquid water potential temperature profiles for both of them in red. And this is in height. This is vertical. And this is the total water, or think of it as water vapor. It doesn't differ very much. The total water profile for both shallow convection and for stratocumulus. And on the right, you have two lines for each one of these figures. The full line is just the determination of the variance based on just counting, just counting, doing statistics and calculating the variance. So directly in that, you would have a curve that represents the values that you would get by estimating the variance based on the relationship that we have over here, right? So we have this relation and we estimate the variance based on the gradients of the mean. And so you could also say, well, okay, so what? So we can see that the approximations are reasonable in these sort of smaller scales for these marine PBL cases. But where do you go from here? And what I would like to highlight is a couple of things. So if you look at these approximations again, they are extremely powerful in a way because they relate the vertical structure with the horizontal variability. So they relate two things that we often don't measure at the same time or don't measure in the same way or with the right resolution. They tell us something about, this is sort of the first order approximation of an attempt to relate the vertical structure of the boundary layer to its horizontal structure. And so it's really about the interaction between the mesoscale and the vertical structure, mesoscale in the atmosphere. But one thing that you can, one way to think of it is, as well is that these are very important tools potentially to extract more information from observations. Imagine you have observations of the mean structure. So let's say the mean value of temperature at a few different heights. Having this relationship and being able to measure the variance at some scale would allow us to add information to what you extract directly by observing the temperature. So one example to show that, and this is very simple and still very sort of first order attempt to do that. But what we try to do here is to reconstruct, again using LES, reconstructing the mean thermodynamic profiles from variance profiles. And so in full, you have the full LES value, for the mean of molecular water potential temperature. This is for the stratocumulus regime. This is for the shallow convective cumulus regimes. The full line is the LES truth, let's say. And the dashed line is the reconstructed values of the mean profiles from the variance profiles using these relations over here. And then you see that the results are far from perfect. However, they're actually pretty good in some regions. And it does tell you that there is information contained in the variance that can be used to reproduce the mean. Now, again, this is not necessarily news, but it does provide a connection between two different levels of observation of the same quantity that could help us build more confidence or provide more sort of pieces of information for this. Now, the science questions that I've been talking about, or the science problems that I've been talking about, are really about the interactions between mesoscale processes and the PBL vertical structure, all of them. And in a way, what I try to do is to introduce the notion of what sort of resolution would we need to sort of tackle some of these problems. And all of these problems are sort of important problems in modern day boundary layer physics, particularly over the ocean. All of this that I've been talking about is over the ocean. Now, going into the mission itself, or the PBL, can you hear me? I'm having an issue with my headphones.
Yeah.
You can. Okay, sorry. I apologize. Let me know if there's a long silence. As I mentioned, about 4 or 5 years ago, 5 years ago now, we had been together for a year putting together this sort of PBL NASA report. And there are a few critical things that I've summarized here. One is that in sort of accordance with the decadal survey, the essential geophysical variables that we identified to address the 4 science goals were better PBL profiles of temperature, better PBL profiles of water vapor, and PBL height, mostly from the profiles of water vapor and temperature. And this idea of the science state stability matrix, in which we sort of start from the left with science and application questions, end up at the end with sort of the measurement requirements. This kind of exercise leads us to sort of the following measurement requirements, which I touched on when I talked about some of the potential science questions that we're looking at. One is the idea of having vertical resolutions that are as fine as 100, 200 meters in the vertical, horizontal resolutions as fine as 1 kilometer, and temporal sampling, which I didn't talk about, because it can get complicated depending on the science question. And a lot of the questions that I was talking about before were over the ocean and were slightly steady state questions. But temporal sampling give at least 4 times per day. Now, I wanted to give you just one example again about the sort of stratocumulus to cumulus transition, because I think in many respects it encapsulates a lot of the physics that is important in the boundary layer over the ocean and subtropics. Now, boundary layers are much more varied than this, of course. Not everything is transition from stratocumulus to cumulus. But I wanted to put this slide here because of 2 things. I wanted to highlight 2 aspects, right? So we talked about vertical resolution of 100 meters, and you can see, you look at this figure. This figure reproduces, so this is vertical altitude, this is the potential temperature. Each profile comes from a radio sonde across this transect. This transect, you can see it very well, but it is from California, from LA to Honolulu. And each color corresponds to the colors over here. So the red profile is over the stratocumulus regions. And as you move towards Hawaii, you go into the blue. And you can see that the boundary layer transitions from a fairly shallow, very well mixed boundary layer with a very strong gradient, a very strong inversion, to later on a boundary layer that is populated by cumulus clouds that probably start around here. That would be the cloud base, and then would end up over here. That would be sort of the boundary layer top. So the boundary layer is much deeper, has a more complex structure, has a much less intense vertical gradient, and sort of much less strong inversion. And there's 2 points I want to highlight with this. So I think we all agree 100 meters is something that is very important. 100 to 100 meters would be very important to achieve from space. But 2 things. One, each regime or case, the number of required independent pieces of information may actually be not that large. So one thing to keep in mind is that the boundary layer, in many respects, is often defined by a number of independent pieces of information that may not necessarily be extremely large, right? So you can see it from here that's the case. The critical aspect here is that different regimes, not only, of course, over the oceans and over the subtropical ocean, but all across the world, will have different requirements. And that's part of the reason why we need this resolution. So on the one hand, we need the resolution because even if we need independent pieces of information that are not, the number of those don't necessarily need to be very large, you need to capture the gradients very well. So for that, you need to be able to measure with high vertical resolution, but also that this independent pieces of information, these degrees of freedom, can be very different from regime to regime. And we want to have a global observatory, so we need the resolution for that as well. Now, getting into the observations, this is a table that I'm not going to get into any details, but you can look at the PBL report or our advanced paper, and you have the table there. You have information about sort of different approaches, different technologies for observing temperature and water vapor from space. Some already implemented, some looking towards the future, and you have some of the characteristics, including the resolution. The best way to show this and to discuss this is to look at the next figure, where we show the same thing, but in sort of a schematic way. So in the horizontal, you have horizontal resolution. In the vertical, you have the vertical resolution. For PBL height, it's just over here, it's just horizontal resolution, but we can neglect that for the moment. In pink, you have the kind of potential horizontal vertical resolutions that are either achieved right now or potentially achievable in the near future using different technologies, different methodologies. In blue, you have other types of observations, either in situ, so measuring something locally, surface remote sensing, or airborne remote sensing. For space-based ones, we have 5 different types. One is hyperspectral infrared, the other one hyperspectral microwave. So the idea is to try to, resolve the spectra on infrared, for example, very well, so such that you can have information of temperature and water vapor at different levels in the atmosphere. So you can think of spectral resolution as akin to vertical resolution. This one here is radio occultation, and I'll mention briefly the fundamental physical principles behind it. This involves measuring GPS signals as satellites move around the Earth and using that to study the refractivity of the atmosphere, and as such, it's vertical thermodynamic structure. And these ones over here are sort of active instruments like LiDARs and radars. And these are the differential absorption LiDAR, differential absorption radar. They basically try to measure the signal, let's say a radar signal that comes back to the satellite at different frequencies, and such estimate the amount of water vapor. The important thing about this figure, the critical thing about this figure, is that you can see that the measurement requirements that we came up with and that Carol's survey already hinted at, of 1 kilometer horizontal resolution and about 100 meters in the vertical, are completely outside these pink boxes, right? So the critical challenge is, how do you actually combine these different technologies to achieve the measurement requirements? Because the reality is that there is no single technology that is able to get us 1 kilometer spatial resolution and 100 meters vertical resolution of temperature and water vapor. It has to be a combination, some sort of intelligent combination of these different technologies that takes us there. Now, in summary, in terms of observations and what is required and what we expect to utilize for this global PBL observatory would be infrared and microwave sounders with high horizontal resolution in low Earth orbit constellations, not too dissimilar from what already exists, but with much higher spatial resolution, and in the case of microwave, much higher spectral resolution. Radio occultation, which I just briefly mentioned, but most likely what we would need is larger constellations of receivers, and I'll touch on that as well. For the differential absorption dial and those LiDAR and the radar, it's unclear if we would be able to have them in low Earth orbit or in suborbital only, in airborne observations only. I'll tell you what the current thinking is in the next slide. And there's three other things that two of them, one of them I will not mention again, but the fifth and the sixth I will. One thing that is very important is that while we're doing this, both NOAA, EUMETSAT, and the Japanese Meteorological Agency, or Space Agency, they are either deploying or planning to deploy geostationary hyperspectral infrared sounders that provide much higher spatial resolution than the current infrared sounders in LEO, and provide information every half an hour. So EUMETSAT already launched theirs. It's not yet producing data, but it will soon. Hopefully, we follow by the Japanese and by the US. Now, surface and suborbital observations I'll mention, and of course, it's going to be essential that PBL physics modeling and data science plays a fundamental role here, and I'll touch on that as well. So this is, let me give you where we are in sort of our broad current thinking from a somewhat programmatic, very high level programmatic architectural perspective for a PBL mission. The critical point here is that the differential absorption radars and LiDARs are likely, or would be likely, complex endeavors, in the sense that to deploy them in space would be much more complex than with the other instruments. They would cost more money, and it would be riskier. In that context, and it's not, I mean, the door is still open for things to be different than that, but as of right now, I think there is an agreement that a combination of infrared, microwave, and radio occultation based on space would satisfy the measurement requirement. If that is the case, then an implication would be that DAR and DIAL would fly in dedicated suborbital campaigns prior and during the mission. And that is very strong synergy between orbital, suborbital, and surface would be critical for the mission. Now, I'll touch on that in the next slide as well. This is actually a critical part of the entire story as we're thinking about it right now. Now, one thing to highlight that until very recently, international partnerships were very important for NASA, and national partnerships, of course, should be very important for the federal government. There's two aspects here that are relevant, and I'll mention. One is that this need for multiple instruments opens the door for partnerships, not only between NASA centers, but between different parts of the federal government and private industry, of course. The other part is that given the strong focus on surface and suborbital components that we want to achieve, this really opens much more possibilities for partnerships with either different US agencies or countries that may have great resources for surface and suborbital, but they don't have the budgets or the resources for space-based assets. So I think this sort of overall concept of the mission of the observatory allows this multiple partnerships that could be extremely beneficial for science. So if we think in that sense, if we think in the sense of the strong focus on the synergy between orbital, suborbital, and surface PBL remote sensing, then we need to focus on specific regions and regimes for these dedicated suborbital campaigns for the duration of the PBL mission. So the idea here is that the airborne component wouldn't be a thing on the side that could help to do calibration, validation, and sort of smaller jobs, but would rather be an essential component of the mission. That the suborbital part will be an essential component as much as the space-based one. And this is sort of a shift in the culture that would be necessary for us to be successful in this endeavor. Now, this would also imply that strong synergy between orbital, suborbital, and surface observations would imply that we would have to come up with joint products, right? We need joint products to highlight the value of this combination. But to do that, we would need very sophisticated algorithms, right? We would need sophisticated data science to be able to combine not only the multiple space-based instruments, but also this with suborbital and surface observations. And of course, as I mentioned, all of this opens the door for a variety of partnerships. So it will be a different mission in many respects. I'll give you, before I close, I'll give you 2 or 3 examples of some of what we're doing right now in the direction of getting to this global PBL observatory. I mean, it's going to be a long way still, and the next decade or so is going to play a fundamental role. But the first thing I want to highlight is that we are already using current program of record data sets that are assets that are in space, measurements that we get right now that don't necessarily have the right horizontal resolution, don't necessarily have the right accuracy, but we're trying to combine them to try to explore this merging of sort of 100-meter vertical resolution instruments with about 1 kilometer horizontal resolution instruments. Now, to be clear, infrared right now does not provide 1 kilometer horizontal resolution. It's about 13 kilometers, 14 at best. But let me talk a little bit about the GPS or GNSS-RO. So radio occultation is a concept that is actually developed initially at JPL when for the Mars atmosphere, when they were when the flybys even in the 60s were flying by Mars and communicating with Earth, and the radio signals go through the atmosphere of Mars, and you can actually measure the reflectivity of the atmosphere at different levels, and that's where the concept was born. That's how the concept was born. So in the atmosphere, this is done regularly now, and this data, a lot of this data is assimilated operationally in weather prediction models. So the idea is that you have a bunch of receivers that get the signal from GPS satellites, and as they are in occultation, so they're moving to the other side of the planet, let's say, a lot of those waves would go across the atmosphere, and depending on the thermodynamic structure of the atmosphere, the reflectivity properties would be different, and they can measure this with very high vertical resolution. And so high that in this case, for example, so this is one example of a good retrieval of specific humidity or water vapor from GNSS-RO compared to a balloon, to a song. And so in blue, you have the retrieval from space, and in what is this? Violet, all right, I'm not good with colors. So in this other color with the little balls, is the radiosonde. And you can see that there's very good agreement. I mean, of course, this is an example where there is good agreement and good penetration, meaning that there is good signal to be measured as the signal goes through the atmosphere, even to very close to the surface. And you can see that when the signal is good, it's radio occultation, the technology is able to measure water vapor within 100 meters of the sea surface. This could play a fundamental role in a lot of what we try to do in terms of estimating latent heat flux, evaporation, and for temperature sensible heat flux. Because a lot of what we do now from space, as far as I know, and I'm, many of you are professionals on this, I just read the papers, but a lot of what is done right now for surface fluxes relies on observations from infrared or microwave, which have a much coarser vertical resolution, or reanalysis, which is a different beast in many respects. This would provide, so radio occultation would provide observations very close to the surface. I mean, 100 meters, I know it's not 2 meters, but we won't be able to measure 2 meters above the surface. But if we can say very often what the values of water vapor and temperature are within 100 meters of the sea surface, that would be, I would suggest, a very important step forward to getting better surface fluxes. Now, what the infrared does, and what I'm highlighting here, is that the infrared provides context, three-dimensional context to the radio occultation. That's why we're trying to merge the two together. And why is that? Well, the big problem, there's two issues with radio occultation. One is the sampling. It's sparsely sampled. I think, as far as I know, it's about, per receiver, it's about 500 profiles per day if you use just the GPS constellation. And many of those profiles don't penetrate the boundary layer very well. So there aren't many of those. And also the horizontal resolution is very coarse. It's basically, imagine a line of about 100 kilometers or 200 kilometers. Infrared, even today, provides full day coverage by many of the satellites that exist, almost full global coverage every day, and provides observations every 15 kilometers or 13 kilometers and a half for the case of hairs. So here in this picture, you see this is latitude, this is longitude. In the middle, you have this box, which is the radio occultation, what we call a tangent point, and you assume that this is the point where the observation is taken, which is not really correct, but that's an approximation. And then you can see that the infrared will provide context in the horizontal, and try to combine those two types of observations to see if we can get good vertical resolution, good horizontal resolution as well. This slide is just to give you an example of how often you actually have collocations between infrared and radio occultation. So this is basically collocations of GPS. I think this is cosmic and Earth observations within 1 hour and 100 kilometers. And there's a few, they're not enormous, it's not an enormous amount, but there's quite a few. And for each one of this, so there's a really red cross, and the red cross corresponds to the radio occultation, and then around it there's about 30, 40, 50 infrared soundings, and what we're trying to do is combine them. And in this slide, the next slide is, please don't even try to, the goal is not in any way to try to be clear about what we're trying to do here. There's too much information, and in a way I apologize for that, but the idea here is to combine microwave observations with infrared and with radio occultation. And if you can focus just on the middle bottom profile, this is again in a vertical, this is specific humidity of water vapor. And all of this, I'm not trying to be clear, but I mean, to be clear, you're not supposed to extract any specific information about each one of these profiles, but each color corresponds to different observations that we're trying to merge into a fused product. And the goal of this slide is to just highlight the fact that we're starting to do this with the current observations to pave the way for the future observations of radio occultation, infrared, and microwave that we'll try to bring together. To do that, and I mentioned this a few slides ago, we will need sophisticated data science. We need sophisticated retrievals, assimilation, data fusion, and AI algorithms that we're already using, and I'll show you one example in my last slide. So second from last slide is one example of the differential absorption radar. So here, as I mentioned before, what we're trying to what the instrument tries to measure is reflectivity at different frequencies, knowing that the differences are going to be essentially due to the amount of water vapor between, let's say, the cloud droplets and the instrument. And in this case, all of this is the instrument already exists and has flown on an airplane, but this is based on LES. These are sort of simulation experiments. This is a shallow convection case, like the puffy popcorn clouds I've shown you. Over here, top left is liquid water content for clouds and rain. These are sort of the popcorn clouds and its associated rain. Below that, you have the simulated observed reflectivity. This is again all simulated using LES. And from the simulated reflectivity of different frequencies, we can extract water vapor profiles that we compare to the LES truth profiles. And you can see that the data retrieval is the blue, and it matches really well what the sort of the truth, so to speak, profiles are. And again, here, two things to highlight. One is sort of not only the accuracy, but also the vertical resolution of DAR. So DAR will be able to tell us in cloudy conditions what the amount of water vapor is, and in practice also what the temperature is if it's sort of liquid clouds. But the other aspect is that it would provide water vapor within, again, about 100 meters of the sea surface, which would be extremely important for measurement of surface fluxes, at least better than what we have today. I'll skip the next slide and I'll go to the conclusions so that we can have a little bit of time for questions. So we're moving toward the global PBL observatory. NASA is focused on this new PBL thermodynamics satellite mission. What we want to achieve is high resolution, 1 kilometer horizontal, 100-meter vertical for temperature and water vapor PBL profiles. And the critical question today, and for the several few years while we tried to build this mission, put together this mission, this sort of coalition of people interested in the mission and willing to contribute, is how do you actually optimally combine these sort of diverse technologies to achieve the measurements that we require? So anyway, thank you.
Thank you so much. So that was great. We have a little bit of time for questions. So I see Yolanda Sarah has her hand up.
Yeah, thanks a lot. That's a really interesting talk. I wondered about, so you're talking a lot here about radio occultation, and right now, Cosmic 2 is in the tropics, and I think it's Planet IQ and Spire are providing the Arctic profiles. Those are the two data buys that NASA has. And I think Planet IQ has a pretty good signal to noise, but I think Spire, some of these companies reduce their signal to noise quality because it's not stipulated in the contract. So I'm wondering, with all of this and your need for certainly trying to get the boundary layer from the radio occultation, you need a good signal to noise. Is NASA going to be then requiring from their data buys this, or is this going to be more that we're going to start funding Cosmic 2 to continue to make these measurements so that we have the data we need? Like, I don't know, like, how is this going to affect those commercial data buys, I guess?
So those are really, really critical questions for which there is no answer right now. We are not at that stage yet, right? We are at the stage of trying to think about how do we move forward in combining infrared microwave and RO. What RO observations would be used, that's still not determined. Now, I think there's a good case to be made that this could be one example of how sort of commercial data, as we are calling it, could be particularly useful. It is possible, and I'm not speaking on behalf of NASA in this context. I don't make these decisions. I don't control the funding, and I don't think these decisions have been made. But I think there's a sense in the community that there is a strong possibility that commercial data could play a big role here. For that to be the case, of course, what you're saying would probably be necessary in a sense, right? I mean, we would need to have the best quality data. We would need much better penetration in the boundary layer than we have now, and to exploit the ability to observe temperature in water vapor, or temperature or water vapor with high vertical resolution. That's all I can say. I mean, there's, on the table, I mean, I don't know if they're public already, but there are 3 white papers that either should come out very soon or are already available publicly. I'm not 100% sure. But in the cloudy PBL white paper, at some stage in sort of the last page, we discussed the possibility of having dedicated satellites and RO receivers in combination with infrared and microwave hyperspectral deployed. That's only one example of what could be achieved, and that's only to explore sort of how far we could go in terms of collocation and all that. I'm sorry I can't give you really a more precise answer, because we don't know what the precise answer is for that. But there's no question that what you're saying is critical, and it's going to be part of the conversation for sure.
Okay, thank you.
Thank you.
There's a comment in the chat from Rick Danielson. Merging measurements, all of which can be considered partially resolving of PBL processes a priori, using a measurement or data model to approach merging, might work in parallel here, though it's not clear how this works into existing sophisticated approaches.
I'm sorry. Was that a question?
Yeah.
Yeah, please go ahead.
Yeah, maybe a comment on existing sophisticated approaches is all I'm referring to here. And no, it's not really a question. Well, it's a question to the community, I guess. But when we talk about these sophisticated approaches of AI and machine learning and so on, they're based, or at least the loss function seems to be based on a simple data model, and that's the expression of. It can be used the data model can be used as an expression of how all measurements are partially resolving of PBL processes, but we don't really play with the data model too much. So it's not entirely clear how the loss function would change, or how the approach would change if we did.
So,
but it's not a question; it's sort of a comment. It's
yeah. Sure. No, I agree. I mean, let me just be clear. I can go back a slide.
Mm-hmm.
When I say, I'm trying to summarize a lot of thoughts in one sentence that fits with font, 20 Arial 24 that fits in a line, on one line. Sophisticated approaches doesn't mean necessarily explicitly AI, right? I mean, there's a lot of incredible stuff that we do with data simulation and retrievals. It's a combination of all of these things. It's quite obvious that AI is going to play an important role. I actually don't. I mean, so I have an example here of what AI can do, but I'm not in any way suggesting that that the word sophisticated and AI comes together. I mean, it comes together with data fusion, simulation, retrievals, and so on. And I don't think we know exactly if, even in current retrievals, I mean, we're using machine learning for some components and physical retrievals for others, and trying to combine them in a potentially useful way. This is just one example. I'm sorry, I'll show you this some other time. This involves machine learning and trying to extract information from water vapor to get temperature. But yeah, I'll skip this because we don't have much time. So I'm happy to entertain more questions if you want. Or
thank you.
Yeah, I see we are over time, and I know people are having to leave, but I see Roger Samuelson has his hand up. So Roger, go ahead, and that'll probably have to be it.
Thanks, Sarah. I know we're late here. Just a quick question. You mentioned in the observables the profiles of a couple of thermodynamic quantities, and then a third, which is PBL height. And I'm just wondering physically what that is and what that measurement would be.
So the Teixeira survey is open about that, right? It doesn't tell you how you measure. There's different ways you can measure PBL. One, I don't know what's the best slide to show you this. Doesn't really matter. But this slide, this one is not too bad over here. This one is not too bad. So one way to think about it is to say that the PBL height is, as it is, the place where the height at which there is strongest gradients that basically separate the turbulent layer of the atmosphere from sort of the more quiescent atmosphere, right? So we know that, for a stratocumulus boundary layer like this red one over here, I hope you see my mouse, the atmosphere will be very turbulent here. There's a cloud over here. You can see the gradient. The cloud base is around here, and then the cloud stops there. And there's a lot of turbulence here, and over here there's no turbulence, right? So the PBL height is really the height at which there is an interface between the turbulent layer and the non-turbulent layer. And that can be found by where the strongest gradients in temperature and or water vapor are. Now, we could argue, and I think that's the story that we are telling people, and that's the way we're thinking about it, is that if you measure profiles of temperature and water vapor with high vertical resolution, then if the resolution is about 100 meters, that's sufficient to be able to determine the PBL height to a very good degree of accuracy. That doesn't mean that measurements of PBL height using other instruments that, for example, are able to capture the aerosol signal wouldn't be useful as well. But I don't think it is implied in either the decadal survey recommendations or the report that you need to go beyond measuring temperature and water vapor. So the assumption is if we measure temperature and water vapor with enough high vertical resolution, 100 meters in this case, then you can extract the PBL height as the strong gradient in those quantities. Now, sometimes it's not that easy, right? So the gradient, when you go to the shallow convection, the gradient is much weaker. And sometimes it's not clear that there is a gradient. But the same thing happens when you're looking at aerosols of cloud, right? Sometimes the aerosols are above the boundary layer and they don't really tell you anything about where the boundary layer is. So there are, different ways of approaching the problem. But I think that there is an agreement that the best way is to measure where these gradients are, because these gradients really, one thing I didn't mention, which I apologize for taking 30 seconds more. One aspect I didn't mention, I was thinking last night that I should, and I end up not doing it, is that the fundamental reason we're measuring temperature and water vapor is because temperature and water vapor control the buoyancy and the boundary layer in the atmosphere, right? It's the differential values between water vapor and temperature in the location and the nearby points in the horizontal that determine how buoyant a particular parcel is or not. And that buoyancy, because most of the atmosphere is so, well, the boundary layer is often so convective for a variety of good reasons. Buoyancy plays a fundamental role, right? You have turbulence because you have shear or you have buoyancy. We have buoyancy that's determined by temperature and water vapor, connected to other things, but essentially by temperature and water vapor. So the structure of temperature and water vapor is what you need to measure to understand what the convection is, which basically is what sets stage for the cloud and sets the stage for the dispersion of pollutants and also sets the stage for where this boundary layer height is going to be. So long story, sorry. The short answer is, and I made it long, we plan to determine the boundary layer height by measuring the gradient of potential temperature and water vapor. And we believe that's the best way to come up with estimates of boundary layer height.
Okay, thank you. That makes sense.
Well, thank you so much. This is great. It stimulated lots of discussion. I'm sure people will have more questions to send via email.
Yes, please feel free to send me questions. By the way, there's going to be a PBL, NASA PBL DSI meeting in Pasadena in mid-May. I think it's the 12th and the 13th, if I'm not mistaken. If you are interested in attending virtually or otherwise, and you're not on the list, feel free to send me an email and I'll send it to someone that will put you on the list and you'll be informed of this meeting and future meetings. Thank you. Thanks for the opportunity.
Thank you.